free vibration system. And we're going to look at springs in parallel configuration and springs in series configuration. But I have some unfinished business to do. Okay, so yesterday we talked about natural frequency, or sometimes it's known as resonance, resonant, N-A-N-T, frequency. And this is what we have written, omega n. And omega n is basically K over M. And the units is in radians per second. And we did an example yesterday where we have what? A mass, remember? A mass, we have what? 10 kilogram. And then we have a stiffness or spring stiffness of 250, right? And then we calculated that omega n is equal to 250 over 10, and this is equal to 5 radians per second, okay? And what happened next is the embarrassing moment, okay? But rather than embarrassing, I went to see what went wrong, and I know what went wrong, okay? So now if we have an axis over here, and I'm going to plot this as 1, 2, 3, 4, 5, 6, 7, 8. On the x-axis is omega, and this is in radians per second. And on the y-axis is our amplitude. Bear with me. So I want you all to have a look on what happened. Okay, you have seen it briefly yesterday. What happened when we do this? Okay. So I know, oh, this is not working at all. That's why I love cooking show, you know. The food always tastes good. Okay. See how much. The most important thing is I want you to see the graph. Okay. And I want to change some numbers. So we have seen this briefly before. Where's the number to change? The number to change is over, okay. Right. So the number to change is here. Okay. If I put 1, right, the thicker line is the system's response. And when I put 1, right, we can say that this is as good as over here. Am I right? So this 1 that I put is a disturbance. So I put a disturbance into the system. And if I change this to 2, you will see that not a lot of change, right? Can you see what I'm changing, yes or no? Right? And then when I go to 3, nothing happening. And some of you say, Eugene, your equation might not be working. And then we go to 4. Again, we have a bit of increment, not a lot. Then we go for 4.5. 4.5, also not a lot. Then we go to 4.9 is coming up. All right. Then I go to 4.99999. Can you all see what happens? Okay. So the amplitude is increasing. Okay, the amplitude is increasing and it's going to be, this is a transient state. I was looking at the transient state, pardon me, okay? But if you look at the later part of the graph, right, is, I think it's Excel playing me up. Let me go back to 4.5. If I go back to 4.5, see, it's not computing, is it? And if I go back to 3, okay, wait, 4.5, 4.8, 4.9, okay, 4.99999. You can see what happened at 4.999, which is close to 5. What happened? The amplitude just went what? High. Yes or no? So after that, if I do 5.2 or 5.1, it's still a bit high. Or did it compute? I think it did compute. Or did the graph refresh? See, the graph not refreshing in time, okay? So it's freaking Excel. 5.1, it dropped down. And then if we go to 6, you can see the whole thing comes down, okay? So if you go to, if I do one more time, if I go to 8 or 9, okay? Now this is 9. You can see the whole thing just mellowed. So what we realize at this line, okay, at this line, we're going to draw a line vertically down on the 5. This is known as our resonant frequency or our natural frequency. So how the system will behave is, we saw this goes pretty flat, pretty flat, pretty flat. And once it's reached the resonant frequency, it goes what? Theoretically, it should go what? Infinite, but it did not go infinite. Okay, it does this. You can see for yourself. Okay, so that's how the frequency responds once it hits resonance. Okay, you can see some examples. You guys seen, I mean, most of the time in your physics class in high school, you see someone singing very at a high pitch to a glass. What happened to the glass? Shattered. For this reason, the amplitude get higher. When the amplitude get higher, the deflection get higher. When the deflection get higher, what happened? Stresses get higher, and when stresses get higher, boom. Okay. Not necessarily louder, okay? It's the frequency. Are we clear? I repeat again, not necessarily louder, okay? If it's louder, it's guaranteed, but it's way too soft, you can't, but not necessarily. You have to hit the right resonant frequency, okay? So this is what I want to go about regarding natural frequency. So yesterday, where we finished off, right, we were deriving this system, which is known as the undamped mechanical system. And then I'm going to continue from here to look to determine the constants, okay, which is pretty straightforward. Let me finish off this example. So yesterday, we write through here, right? Then we were going to find the values of C1 and C2, right? So we're going to substitute. So I'm going to call this equation over here that we have yesterday, equation 1. So we're going to substitute y is equal to 0.15 meters when time is equal to 0 seconds into equation 1. So this is 0.15, which is equal to C1 cos 9.905 multiplied by 0 plus by C2 sine 9.905 multiplied by 0, square bracket on the outside. So what you realize that C1 over here is equal to 0.15. Okay. And then from here, we know if we do, we're going to substitute dy by dt or y dot, which is equal to 0 when time is equal to 0. So when we differentiate this, so we have y, dy by dt. So this will be equal to minus 9.905 C1 sine 9.905 t, right? And then we have plus by C2 9.905 cos 9.905 t. And then when we substitute everything in, if this is 0, this is 0, and the time over here is 0, no doubt this is 1, the left-hand side is 0, we realize that C2 will be equal to 0. So from here, our particular equation will be equal to 0.15. And we are going to have, that's our C1 and cos 9.905. Okay. So this is our answer. And this is in meters. Okay. And remember, I like to emphasize again, okay, students tend to make a lot of mistake over here. When you calculate this, make sure your calculator function is in radians. Okay. Okay. Today, yesterday in lecture, I taught you all how to draw multi-body free body diagram. And I taught you guys how to draw, assume your what? Reaction forces, okay? Are you all comfortable with that? Yes or no? Okay, if it's not comfortable, you're confirming an approach. Okay, today we're going to deal a lot on this sort of problems, okay? Right. So the next thing that we're going to do, okay, I'm going to sketch the free body diagram of a undammed undammed system. Okay, so into a free body diagram. If you have any question, just say excuse me, okay, because I'm writing. Yep. A pint. Thank you. Hey? No. We only drink at night. And towards the end of term, okay, I'll buy 48 cans and I'll distribute you cheeky sort. It's too early for that, okay? I will love one also, okay? Right. So if we look at the free body diagram of an undammed, I want you to get used to drawing free body diagram, okay? Undammed mechanical system. Is that why you come to my class? There's free beer. That's why I attend all my lectures in England. You're free beer for crying out loud, okay? So what we have over here, if we have a mechanical system, an undammed one, undammed meaning that there is a what? A spring and a mass only. Okay. Yesterday, a student asked me a very good question. In a mechanical system, you can do without a damper. I repeat again, in a mechanical system, you can do without a damper like this. Okay. However, in a mechanical system, you cannot do without a what? Spring and just have the what? Damper. You understand what I mean? So I'm going to tell you what is impossible. It's impossible to have this in a mechanical system. Okay? It's impossible. Why?